3.7 is about interpreting graphs. The first thing you always want to do is determine what function your graph is giving you. So determine whether the function is f or f prime. Since they're always labeled, and depending on which function it is, our interpretation will come a little differently to us. Okay, so if our graph is f prime, we're going to make a number line and interpret from there, which should tell us things like increasing, decreasing, relative min, and max. From there, we'll make our second derivative number line, and we'll use the graphs to interpret from there. So let's flip this over to the front side and see what we're starting with. So my first graph here is the graph of f prime. So I'm going to make a number line underneath for f prime. My number line is really just my x-axis here. So I can see I have some x-intercepts. They're not perfect, so we're going to just kind of estimate here. So over here, we'll call this about 2.4. That's a 0 of the derivative. This will be about negative, just call it 0.7, a 0 of the derivative. And then over here, 1, 2, 3, and a little bit more. Negative 3.1, 0 of the derivative. Okay. Now, when a function is above the x-axis, it's said to be positive. So in the region before, f prime is positive. When a function is below the x-axis, it's said to be negative. And then we have positive, back to negative. So now we just do our interpretation of f prime. So everywhere where f prime is positive, f is increasing. Everywhere f prime is negative, f is decreasing. So we're going to fill in those intervals here. Okay, decreasing on the other intervals. So any relative mins or maxes. So I have a minimum when my derivative changes from negative to positive, since that means my original function would be decreasing and then increasing on this interval. So a relative minimum when x is negative 0.7, and maximums of the other values when my derivative changes from positive to negative. So going into concavity, we need our second derivative. So obviously this is still our first derivative graph. So we're going to have to come up with a number line for the second derivative based on this. So this is just a little tricky, but all you have to do is remember, how do I get from one derivative to the next derivative? How do I get from one function to its derivative? I look at the slopes of the tangent lines. So the slopes here are all negative until I get to the minimum, which is when x is negative 2. So negative 2, the slope of a tangent line there would be 0. That's a 0 of the second derivative, and all the tangent line slopes before are negative. After that, they're all positive until I get to the x value 1. So at 1, I have another 0 of the second derivative, and again, in between, the slopes of these tangent lines are all positive. Okay. After that, we have more tangent lines. Their slopes would all be negative here. And that's how we get our second derivative based off the first derivative. We just look at the slopes of the tangent line. All right, so now we interpret our second derivative for our function. F is concave up when the second derivative is positive, negative 2 to 1. F is concave down when my second derivative is negative. Any points of inflection occur whenever I have a change in concavity, so at negative 2 and 1. Okay, so that's how we do our interpretation when we're starting with the derivative of a graph. In example 2, we're given the original function. Okay, so when we're looking for where is it increasing, decreasing, do you see relative max and mins, we're really just looking at the picture we're trying to fill this in for. So where is it increasing? Well, it's increasing until it gets to x equals negative 1. Anywhere else should be from 1 to 2. Decreasing, negative 1 to 1. And again from 2 out to infinity. A minimum occurs whenever my graph changes from decreasing to increasing. I have one minimum here, one relative minimum when x is 1. Relative maximums occur when my graph changes from increasing to decreasing. So increasing, decreasing happens at negative 1. I also have a change from increasing to decreasing at 2. So this is also a relative maximum. When we get into concavity, remember if it looks like a downward facing parabola, it's concave down. An upward facing parabola would be concave up. Okay. There's a trick though to it here. Remember, this is not a nice smooth turn over here. So you'll notice that this piece of the graph looks like an upward facing parabola, while after that point, it also looks like an upward facing parabola. The graph is still concave up. Okay. Now, we're not going to have concavity here, so we will switch and do 2 intervals for that. But we do need to figure out where does the concavity change here, because this is a nice smooth curve, so there must be a point of inflection in here. So that should happen about halfway between the maximum and the minimum. So I'm just going to go ahead and call that at 0. That'll be where my point of inflection occurs. And then my concavity, concave up. So I'm going to say 0 all the way to 2, 2 to infinity. Concave down would be the first part of the graph, all the way negative infinity to 0. So again, whenever we're given the graph of the original function, we're just interpreting what we see. Okay. When we have the graph of the derivative, though, we're going to create number lines and interpret the number lines to get our results. So example number 3 is, once again, the graph of a derivative. So we'll start with our f prime number line, which is really just our x-axis here. So if I were just kind of looking at my x-axis, I have a 0 at 1. And I have another 0 here at 1, 2, 3, 4. Okay. Anytime my graph is above the x-axis, it's positive. Below the x-axis is negative, and then positive again. Then we just interpret our number line for our function. So increasing, decreasing, increasing. So increasing, negative infinity to 1. 4 to infinity, decreasing 1 to 4. A relative minimum, is there a change from negative to positive? Yes, at 4. A relative max, a change from positive to negative? Yes, at 1. Going to concavity and points of inflection, we need our second derivative. So above, we wrote down to get to our second from our first is just one derivative away. And finding one derivative is finding the slope of the tangent line. So I'll notice the slope of every tangent line along the first part of this function is 0. 0. So just all these values give you 0 until I get to an x value here of 0. So when I get to 0, what happens? The slopes of the tangent lines are all negative until I get to this x value 2. And after that, the slopes of the tangent lines are all positive. Now at 0, we did not have a nice smooth turn. So the function f prime is not differentiable here. So my second derivative can't exist here. So this is a d and e. Same thing at 2. It's not a nice smooth term. So this is also not differentiable here. Okay. And then I'll interpret my results here. So concave up, only from 2 to infinity. Remember, the second derivative tells us about the concavity of the original function f. That's what we're being asked here. Concave down, 0 to 2. Any points of inflection? Well, points of inflection, they do happen when the concavity changes, but in order to have that, the point would have to exist. So although we have a change in concavity at 2, this point does not exist here. So we're not going to list it as a point of inflection. All right. We might add in that we have no concavity on negative infinity 0. Okay, and no POI. So it is different whether you're looking at the graph of the derivative or the graph of the original function, how you'll approach the problem. So be very careful with the two differences.